So when we think about these different cells, I want you to think about a three-dimensional arrangement of these cells. In a simple cell, we have an atom at each corner. So I have an atom at every corner, and when we start stacking them together, where they're sitting together, they share an atom. So if you think about that, if I have a corner atom in a cubic cell, how many cells share that corner? Think of total. Don't think of 1 plus 3 more. How many total share this? Okay. Here's my three-dimensional space. Now we've got an atom right here. How many cells are touching that atom? 8, right? So when we have this, and we have an atom or an ion or whatever it is in the corner, the cell owns 1/8 of an atom at the corner. And how many corners does a cube have? 8. So 8 corners times 1/8 of an atom is equal to 1 atom per cell. So each unit cell in a simple crystal lattice, simple cubic lattice, owns 1 atom. Now we're going to look at this the same way for these other types. On the next page, I have some drawings for you that I reproduced from your text. This is kind of what we think of as a simple cube with an atom at each corner. Now, this is a space-filling model, and this is an important relationship. This shows you that these atoms are actually touching, okay? So if we look at this from the front side, this is one side of that simple cube. I don't know if you can't really see what I drew there. Can you see what I drew there? That this is one side. So if you look at this, what is the relationship between the radius of those atoms and the size of the cubic cell? They are directly proportional. How so? Well, yeah, if the radius is it gets bigger, but the length or the distance of the cell is equal to 2 times the radius or the diameter, right? Because you get one radius here and one radius here. So we can think of the side of a cubic cell is equal to 2 times the radius in a simple cube. And we're going to look at this and think about the geometric relationships because you're going to have to do some messy math with this. Okay, so that's the simple cell. Simple is also called primitive, but I call it simple. The next type is body-centered. And there's a picture here. This is a body-centered where this atom is floating in the middle of that cell. And again, in the space-filling three-dimensional model, this body-centered atom that's right in the middle, it touches the front lower, goes to the middle, then to the back upper. So you can draw a line through the cube from here to here. Okay, if we go from one of these corners down here to up here, across that, and all those atoms are touching. So if I have a body-centered cell, and there is an atom inside this cell, how much of that cell, or how much of that atom is owned by my body-centered cell? If it's right in the middle here. If it's sitting right in the middle of this cube, the whole thing, right? So a body-centered cell has 8 corners with atoms times 1/8 is equal to 1 plus 1 center atom and we own all of it, so that's equal to 1. So it's 2 atoms per cell. So in body-centered, we have 2 atoms per cell. Now, the next kind is face-centered. And you'll see in the three-dimensional drawing here that you have an atom sitting in each face. And if I draw lines from corner to corner, they touch, and corner to corner the other way. So in my cell, I can think of this atom sitting right here. So if it's right here in the face, how many cells share that atom? If it's in this face? 2, right? So if 2 cells are sharing it, then the cell owns half of it. So in a face-centered, we have 8 corners times 1/8 of an atom is 1. And we have how many faces in a cubic cell? How many sides does this cell have, this cube? 6. You know that from shooting dice, right? Okay. 6 faces times 1/2 is 3. So we have 4 atoms per cell. Then the last one is base-centered. Base-centered is just like face-centered, but instead of having them in all 6 faces, we have atoms in the top and the bottom. So we have 2 faces, or 2 bases, times half of an atom is equal to 1, and 8 corners times 1/8 is 1, so we get 2 atoms per cell in a base-centered. So if we think about the ownership, now we can do some simple kinds of problems. On the next page, I've included something that I think kind of shows you these geometric relationships. Now, I took these pictures out of your textbook, and they look a little better in the book than they do here. So you might want to refer to the book, and that might be helpful. So if we look at this, we can think about some of the relationships. You have to know some geometry and a little bit of algebra to solve some of these fancier problems, but they've given you the appropriate information here. We're going to do a simple one first. Silver has an atomic radius of 144 picometers. What would the density of silver be if it crystallized in a simple cubic lattice? It doesn't, but we're going to start with that first. So you can look at those geometric relationships if you need help. But let's think of a simple cubic lattice. We have a cubic cell, and if we think about simple cube, we have atoms at each corner. And I apologize in advance for my drawings. But here's my atoms in the simple cube. These are supposed to be all the same size and all concentric around the corners. And my drawing's not that great, but I think you get the idea, right? So now, if the radius is 144 picometers, how do we find the density? What is density? Mass over volume. So if I know the mass of a cell, how much silver is in there, and I can figure out its mass, and I know the volume, I can find the density. So how do we find volume of a cube? It's the side cubed, or length times width times height, right? So it's the side of the cube, which I'll just call the length, cubed. So what is the length of the side, numerically? 2r. And r is 144. So that's equal to 288 picometers, because this radius is 144, and this radius is 144, even though my drawing doesn't look the same. So 288 picometers. So it is equal to 288 picometers cubed. So the volume of my cell is equal to 2.38 times 10 to the 7th cubic picometers is equal to 1 cell. So I know the volume now. How do I find out the mass of how much silver is in that cell? What do I know that would be useful about a simple cubic lattice? There's one atom per cell, right? So there is one atom of silver per cell. How do I change atoms into mass? Use Avogadro's number, right? We know that 1 mole of atoms, 1 mole of silver, is Avogadro's number, 6.022 times 10 to the 23rd atoms. So my atoms cancel, so I know now moles per cell. And how can I change that into mass? Molar mass. And the molar mass of silver, 108 grams per mole. So I get 1.79 times 10 to the negative 22nd grams per cell. So now I know the mass of a cell and I know the volume of a cell. Now I can find the density. So I have 1.79 times 10 to the negative 22nd grams divided by 2.38 times 10 to the 7th cubic picometers. So that is equal to 7.52 times 10 to the negative 30th grams per cubic picometer. So that's the density of my silver if it were crystallized that way, which it's not, right? But that's just an example, and that is the simplest example. Now, what if you were trying to compare this to water, right? And so you wanted it in some different units. We're used to seeing things in grams per cubic centimeter. So if you wanted to change this, we know that 1 picometer is 1 times 10 to the negative 12th meters. And we know that 1 meter is 1 times 10 to the second centimeters. So that means that there's 1 times 10 to the 10th picometers per centimeter. So if I want to switch this over now to cubic, I just cube this whole thing. So 1 times 10 to the 30th cubic picometers is equal to 1 cubic centimeter. So it would be 7.52 grams per cubic centimeter. So you can switch the units, but never do more work than necessary is my motto. If the question says what's the density, just take the mass, take the volume. Don't try and get fancy. Just chug through it, get her done.